All right, do you see the quiz question now? Yes, no? Okay. All right. Hi. Yeah, so hello. I want to come back to talking about complexity of recursive functions. So we had something like this, right? So we said like if n is small or equal than 2, then we return 1. And otherwise we return feb of n minus 1 plus feb of n minus 2. And the way you generally approach this, should have said something. No? Was almost okay. Okay. So the way we generally approach something like this is we'd say, okay, we'll make a call tree, right? So what would the call tree look like? So we start from feb n, and then when you're trying to compute feb n, what are you doing? Well, you need to compute, did they say record? I shared it. So from here, you would say, okay, when you're trying to compute fib of n, you would be computing fib of n minus 1, and also you would be computing fib of n minus 2. And that's because that's what you're saying here, right? So fib of n minus 1, fib of n minus 2. And then from here, for example, you would say, okay, there's 2 calls. So one of them is to n minus 4, or I guess we would say feb minus 3 here. And then here we would say feb minus 4, because if you're making a call to feb n minus 2, well, this would be minus 3, and this would be minus 4, and so on. So now the task here is to try to count how many calls in total there are. And one way to approach this is to say, well, we have this call tree, so on each level, we'll try to count how many there are. And that's a little bit difficult because here, if you're going over here, so this would be feb n minus 2 and so on. So over here, you're going n minus 1, n minus 2, n minus 3, and so on. On the other hand, here you're going n to n minus 2 to n minus 4 and so on. So the levels are not exactly going to line up. However, you could say, well, like at most, how much is there going to be on any level? And the answer would be, well, at most 1 here, exactly 1 in fact, and then 2 here, and then 4 here, and so on. And if it were the case that all the levels were complete in the sense that it was going like n to n minus 1 here and also n to n minus 1 here, then eventually you'll get to 2 to the k here. And what's k? Well, it's the number of steps that you need in order to get from n down to 1 or 2, which is n. So the answer is at most. So this is the same computation that we had before, 2 to the n plus 1 minus 1. Right, so that's the computation for the call tree where it was just branching by 2 every time. So each call produced 2 other calls. And then eventually you got to 1, and that was 1 plus 2 plus 4 and so on, up to 2 to the n. So that's 2 to the n plus 1 minus 1. Now, that's an overestimate. The reason it's an overestimate is because at the end, there would only be one call at the very top where you went from n to n minus 1 to n minus 2 and so on down to 1. On the rightmost branch, in fact, you would run out of calls at level n over 2 because you go n minus 2 and n minus 4 and so on. You'll get to 1 here, and that would be at level n over 2. So we can say, well, at least if we go by the length of the shortest branch here, that would be like 1 plus 2 plus 4 and so on, plus 2 to the n over 2. Right? So this is assuming that we just count the calls on the levels which are completely full. Does that make sense? Questions? And that's, again, approximately 2 to the n over 2 plus 1 minus 1 using the same formula. So here's a different approach. So how many calls produced by fib of k? Well, the answer is number of calls produced by fib of k minus 1 plus the number of calls produced by fib of k minus 2. Right? That just, like how many calls? Well, this many. And then plus 1, that's the one that's actually fib of k. Make sense? So what I can say is, okay, all right. So that means that if I have a function that I'll name like n fib calls of k, that's the number of calls produced by fib of k, well, that would be n fib calls k minus 1 plus n fib calls k minus 2 plus 1. Right? So this is like a mathematical function that's the number of calls that's produced by fib of k. And I'm saying, like, mathematically, what's that function? Well, just because in order to compute fib of k, well, you need to call fib of k minus 1 that produces n fib calls k minus 1 calls. And then you also need to call fib of k minus 2 that produce n fib calls k minus 2 calls. And then there is the tiny little plus 1 here. So note that this function is basically the same as the definition of the Fibonacci sequence itself. Right? So right? Just because the definition here is almost the same. This is n. The definition here is almost the same as the definition for the Fibonacci sequence itself. And in fact, kind of an interesting thing here is that you can get at it another way. So you can use some linear algebra in order to just prove that fib of n is phi to the n over square root of 5. Rounded, where phi is the golden ratio, if you've heard about that. And phi is approximately like 1.61. So that's interesting. So that means that the Fibonacci themselves are numbers themselves are like 1.61 to the power of n. And then if we look back at this, so this is O of 2 to the n, like we saw before, because 2 to the n plus 1 is 2 times 2 to the n. And then what is this? Well, 2 to the n over 2, that's square root of 2 to the n. So this is like O of 1.41. 1.41 is square root of 2. So that's O of square root of 2 to the n. And in fact, like that tracks because this means that the exact estimate is O of 161 to the n. All right. So going back to this. So first of all, how many coals in total? So the first estimate was, well, we'll just count up using the different levels and we'll overestimate. So we know that the levels are going to be incomplete because at the last level, the only actual fib of 1 coal here that's going to be at level n is the one that goes n minus 1 and minus 2 and so on down to fib of 1 if it's n levels. So it's an overestimate to say that on this level there's going to be 2 to the n. In fact, there's just going to be 1. But as an upper bound, we can say, well, if this level is full, it's going to have 2 to the n coals on. Right? And then we say, okay, like what's a lower bound? And the lower bound is saying, well, we'll just count the levels where actually there are 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on coals where the levels are full. And that worked out to 1.41 to the n. So this is not the upper bound on the runtime complexity. This is an underestimate. And then we had this different way of figuring things out, where the way to figure things out was to say, well, we'll define this function, the number of calls that it takes to compute fib of k, and we'll just write down what this function must be based on our reasoning about kind of the number of calls, which is, well, to compute this, it's 1 call plus all the calls that it takes to compute this, plus all the calls that it takes to compute this. And based on that, we write down this kind of formula. Right? So the call itself plus whatever it takes to compute this for n equals k, plus whatever it takes to compute this for n equals k. And then we just observe that this formula actually kind of looks like the formula for the Fibonacci numbers. So it's going to be approximately, we haven't proven that that's exactly it, but it's like approximately Fibonacci of n. And like we saw, it kind of works out. Yes.
Is the +1 in that n fib calls equation from checking?
No, so it's like the call itself, right? So like how many calls to do fib of k? Well, it's like the call to fib of k. So you can think of it as just like this whole thing. And then inside of it, how many calls? Because if you count as 0 calls, the initial call, well, it's going to be 0 all the way down.
Oh, okay.
Make sense? So, okay. So that is obviously kind of like you have to think about like all of those ways in order to estimate the complexity. You have to think about it. And like sometimes it's very difficult to figure things out in terms of what the complexity is. So I want to give you kind of one example that shows kind of really starkly, I think, how difficult it can be to estimate the complexity of something. So the point that I want to make here is sometimes can't even tell if the code is an infinite loop. And that, of course, like if you can't tell whether it's an infinite loop or not, well, obviously you don't know the computational complexity because, well, maybe it's an infinite loop, so it doesn't even terminate. Okay. So, and this has to do with this idea of, well, so this is like famously Fermat's last theorem states that that'll make sense in the context in which we're talking about in a second. No solution to the equation a to the n plus b to the n is equal to c to the n for n greater than 3. So I'll see for n equals to 2, a, b, and c are whole numbers. So for n equals 2, there are solutions like that, right? So for example, you could say that 3 squared plus 4 squared is equal to 5 squared. That's a solution, right? So in general, so Fermat, I think it was the 18th century. So famously, kind of wrote down a proof that you cannot find a triple of a, b, and c that are natural numbers such that a to the n plus b to the n plus c to the equals to c to the n. And he famously like wrote down, I have found an ingenious proof for this proposition. However, the margin of this book is too narrow to contain it. So it was like written like on a page of a book where it's like, I've proven it, but I'm not going to tell you how. And then it took until, you know, the 21st century for people to actually figure out how to prove it. Okay, so that's the math. So now the reason I'm telling you about this is that you can kind of encode this using Python code. So you can write Python code that's basically going to try and find a solution to this equation. And it's going to tell you if it found a solution, and if it can't find a solution, it's going to be an infinite loop because it's going to keep trying. Right? So how do we do this? So I want to say, okay, so want to try every possible triple ABC and check if a to the n plus b to the n is equal to c to the n. So this is a little bit more annoying than what we had done in the past, because in the past, if you wanted like all the possible passwords, you had like the possible characters in the password. Here, I want to try every possible A, every possible B, every possible C. So kind of unlimited number of characters. So it's not like a password of length k. And there's no limit to what A and B and C could be. But there is a trick here. So the trick would be so return ABC such that A to the n plus B to the n is equal to C to the n for A and B and C between 1 and k. So B is going to be like this as well. And C is going to be like this as well. Okay, and that becomes feasible, right? So here you just need to check like every A between 1 and K, every B between 1 and K, every C between 1 and K. So we know how to do that. So we'll just say, for A in range, so 1 up to K plus 1, and then for B in this range, and then for C in this range. And then we'll just say, okay, so if A to the n plus B to the n is equal to C to the n, return ABC. You didn't find any, so the power, of course, is like this. So if you don't find a triple like that, at the end, you'll just get here and you'll return none. So if you remember, this is not necessary. If a function gets to the end and doesn't return anything, by default, none is returned. Make sense? So, okay. So now we can say, okay, fine. So I can now check everything for all the possible Ks. Or I guess like we can display the triple here. Keep going. Right. So what I'm going to do is I'm going to say, so check for my K, I think is straightforward. And what I'm going to say is like check for my K for K equals 1, and then K equals 2, and then K equals 3, and so on until infinity if need be. So, okay. So now we can run it. And for n equals 2, there is a solution. So for example, 3, 4, 5 is a solution. Okay, not defined. Oh, I didn't send the K. And here it found 3, 4, 5, right? On the other hand, you try to send 5, and it's going to go on forever. Why do I know this? Well, because Andrew Wiles in 2004 or whatever proved that it's going to go forever. I think for 5 it was known before. But the point is, like, it's really difficult. It took like hundreds and hundreds of years for mathematicians to prove that it's an infinite loop. So that suggests that just looking at the code, sometimes you can't even tell if it's an infinite loop because it would take like lots of years of math to prove it. So the point is there's no kind of universal analysis here that could possibly apply. And in fact, provably so. So the fact that you cannot have a universal method for determining complexity or even for determining if there is an infinite loop or not, that has been actually rigorously mathematically proven. If there is time on Wednesday, I'll prove it to you. All right. So the point of this example was both to show this technique. I think it's kind of a neat trick for saying, I'll just try to increase the limit every time. And also to just make the point that sometimes it's just difficult to do anything. Right, make sense? Questions? Wouldn't it be embarrassing if it returns something? No, it won't. Yeah.
Does it work for n equals 3? Is that also an infinite loop?
For n equals, I believe for n equals, yeah. So I said n greater than 3. It's actually, you're right. It's greater or equal. Yeah. Okay. So, all right. So, okay, that's that. So what I want to do now is one more algorithm. This is going to be merge sort. And this is going to be like a fast sorting algorithm. So, well, I've shown you that sometimes there's nothing you can do in terms of the analysis. Here's an example where you can figure something out if you think really hard. So here's the idea for merge sort. So we start with whatever, a list. And then the idea for how we're going to sort it is like this. We're going to split it into halves. And then I'm going to sort this guy, and I'm going to sort this guy. And then once they're sorted, I'm going to put together the two sorted lists. So that means that this one, I'm going to sort somehow. We'll see how. So you'll notice that, well, I didn't actually sort it well, but I could, right? So you'll notice that once it becomes small, it becomes not difficult to sort, right? So you can even do it, well, I wasn't paying attention, but you can even almost do it by eye, right? So now that I'm paying attention, that's now sorted. And the idea is, okay, once this is sorted and also this is sorted, it's easy to bring them together by just saying, okay, so I have like 2 and 2 and 2 here. So I'll write like 2, 2, 2. And then what comes next? Well, it's the 5. And then I have a 10 here and I have a 10 here. So they both are going to go here. And then it's going to be the 12 and then 45 and then 100. And you can kind of see that, like, I did it by hand. It was clearly possible to do, even though if you look at the entire list, it would be kind of annoying to sort. So that's the idea. So to merge a list, basically merge the first half of the list. And then the sorted version of the second half of the list. Right? So that's the basic idea. Split the list in half. So this is going to be the first half, and this is going to be the second half. Then sort the first half and the second half using recursion magic. So like if we have a merge sort function, we can use it on smaller inputs. And then merge them together. So one thing is that you got to be careful that the merge function doesn't ruin things by being slow. So one possible way to write a merge function is to say, well, like in order to create a sorted list that's like L1 and L2 put together, well, I'll just return the sorted of L1 plus L2, right? So I'll stick L1 and L2 side by side, and then I'll sort the entire list. Well, that's not helping. That's just using the sorted function. But if L1 and L2 are already assumed to be sorted, which they are here, you can do something better, right? So you can say, okay, so let's say that L1 is like whatever, something sorted. And then L2 is also something sorted. Then I can say, okay, I'll just make a resultant list and I'll just keep inserting into the list and I'll keep track of where I am in L1 and where I am in L2. Right, so right now I inserted the 1 in L1, so I'm here in L1 and I'm here in L2. So I'll insert the 2. So now I'm here in L1 still, and I'm here in L2. And I still need to insert from L2 because 3 is smaller than 5, so that's going to be That's going to be like this. So now I'm here in L2 and I'm still here in L1. And then I'll just keep inserting from L1. And then I'll finish inserting from L2. So that's how I'll do it. So res initially is empty. And then I'll have the location in L1, and initially it's going to be 0. And I'll have the location in L2, which initially is also going to be 0. And now I'll just keep getting stuff from L1 and L2 while keeping track of like where I'm in L1 and where I'm in L2, and I'll just decide from which to take based on which incoming element is smaller. Right, so we'll fill in the while condition a little bit later. So I'll just say, okay, so if L1 location is smaller than L2 at the L2 location, then what I'll do is I'll insert from L1. So I'll append this guy. And then next time L1 location is going to be larger by 1. Otherwise, we do it the other way. Right, so I keep insert. So I start with L1 location here and L2 location here, and I keep advancing one or the other. And I only insert into result the one that's smaller currently. Since initially the two lists are sorted, the list at the end is also going to be sorted because I keep inserting the small element. So when should I stop? Well, so here I need to be able to check whether this guy is smaller than this guy. So if I ran out of elements at either one, that's not going to work. So it needs to be that L1 location is smaller than the length of L1, and also L2 location is smaller than the length of L2. So once I'm here, it might be that I haven't gotten all the elements from L1 or all the elements from L2. That's okay. I'll just extend the result with the rest of L1 if there is anything. So this is going to be L1 starting from L1 location and up to the end. And I'll do the same with L2. So here I'm using kind of the nice property of the slicing notation that I'm allowed to do that. So if you say like L from 10 to the end, that's just going to be empty. So either L1 location or L2 location is actually equal to the length of L1 or L2, but that's fine. It just means that maybe this is empty or maybe this is empty. It's definitely going to be the case that one of them is not empty because you can't run like if you're taking elements out of two bags and you stop when one has run out, well, they can't both run out at the same time. Make sense? So this is the merge. So how long does that take? Well, what we're doing here is we're going through. So basically, we are either incrementing L1 location or we're incrementing L2 location, but not both every time. So that means that in all, this would be at most in fact, one fewer. Because you are not going to run out of both. Right? So you keep incrementing either the L1 location or the L2 location. You're not going to increment both to the end. So this is this many iterations. And then here, basically, you're going to make up for what you haven't inserted up to now. Right? So in the worst case, however, it would be that you just need to create a list that's almost as long as L2 or a list that's almost as long as L1. Right? So in the worst case, create a list of length less than length of L1 plus L2, which is the same. Right? And that's because this, like, it might be the whole of L2, this might be the whole of L1. Just do an upper bound, like it's not, you're not going to have to create a list that's longer than length of L1 plus length of L2, and extend res by that many elements. So both this component, so that would be proportional to length of L1 plus length of L2, and also this part is going to be proportional to length of L1 plus length of L2. So that means that as a whole, this function is of length of L1 plus length of L2. Right? So the analysis here was this is proportional to length of L1 plus length of L2 at most, because it involves creating a list that's shorter than that. And this is also at most proportional to length of L1 plus length of L2. So as a whole, this function is proportional to length of L1 plus length of L2. And it kind of makes sense because what are you doing? So you have two lists, which together are the length of the original list. And you're just merging them by going element by element. So how long is it going to take? Well, it's going to take time that's proportional to the total length of the two lists. Make sense? So, okay, so that was the helper function. So now we're ready to write merge sort. So the base case is going to be, well, if the list is of length L, it's already sorted. Of length 1, sorry, right? So if the length of the list is 1, the list is sorted. So we want to return a copy rather than the original. The reason we want to create a return a copy rather than the original is because if you return the original and say, oh, that's sorted, then the client, which might be the function itself, might then change the result, and that as a result will also change the original list. That would be unfortunate. Does that make sense? So, okay. So that's that. So now we'll just say, okay, merge the sorted version of the first half and the sorted version of the second half. That's it. That's not the second half. This is the second half. Right? So the way to think about it, like, why does it work? Well, leap of faith, right? So you say, if it works for a small list, so you can use it as a helper function for the larger list. And this is a way to use the helper function that makes sense, because if you sort the first half, then you sort the second half, then you use merge to sort both solutions. That's your answer. All right. So how do you come up with this kind of thing? This algorithm is traditionally attributed to John von Neumann, who invented like most of computer science. So like it's hard to say how to be John von Neumann, but in this kind of situation, you would say, well, something that works often is what's called, and that's again attributed to von Neumann, is divide and conquer. So solve the problem for parts of the input and then combine to form the solution to the original problem. So this technique kind of often works. And this is one of the situations where it just does, in the sense that you just look at it and you say, okay, like, what if I could sort half the list? Would that help? And the answer in this case is yes. It's not exactly straightforward because you'd also have to have the insight of, oh, I actually can merge two sorted lists faster than I could just resort the whole thing. And that it's not obvious that that would be true. But in this case it is. Yeah, so yeah, so that might look like a kind of like a violent metaphor. Of course, John von Neumann, of course, like also invented, well, not invented, but was involved in building the atom bomb, and then was like involved in advocating for using it. So that's like not the most violent thing that John von Neumann came up with. So that's like that. So look it up on Wikipedia. Interesting guy. So yeah. Yeah. Yes. Sorry, I did not say return rest.
Yes, that's sorted list, right?
Yes.
So what's the point of the recursive function?
Well, merge only works if L1 is sorted and L2 is sorted.
Okay.
Yeah.
Now I get it.
Yeah. Okay. So all right. Okay. So let's look at the complexity here. So we start, so I won't say merge sort L, I'll just say we start with L. And then that makes two calls, and that's like half of L, the other half of L. So I'll call it like L1 and L2. And then here again, split L1 into half and make two calls. So I'll name it like L11, L12, and then split this guy in half. So this would be like L21, L22, and so on. So this is those calls. Now, and this is like, so for example, like L21 would be the first half of the second half of L, right? So L2 is the second half of L, and then L21 is the first half of that. So what I'm going to do in the next 2 minutes is count the calls, which in this case is not going to be enough. So on Wednesday, we'll complete this. Well, L is of length n, and then L1, L2 are each of length n over 2. And then L11 and L2 and so on are of length n over 4. So I'll say each list of length n. And then here it would be each list is of length n over 2. And then here each list is going to be of length n over 4. So that means that there's going to be log to n levels. And then the usual computation, right? So because log to n levels, because you go from length n, length over n over 2, length n over 4, and so on. So in general, that's going to be 2 to the 0 plus 2 to the 1 and so on, plus 2 to the log to n calls. We already have this kind of computation. This is one of the shapes that we know about. So that's equal to 2n minus 1. That's just the computation from before. That does not mean that this is all then. It does not mean that this is all then, because merge doesn't take a constant amount of time. So it's not the case that each call takes the same amount of time. We'll have to do more work in order to see that the complexity is actually analog n. Next time, I'll see you. Thank you. Yeah, so sorry, so I just want to point out, so on Piazza, there is links to notes. So all the lectures are, of course, like recorded on YouTube. There's also notes now, and there is lab solutions to the extent that they're useful. Like ChatGPT knows the solutions too, to be honest, but yeah. Oh, I thought people said that it's there. Can you refresh? Great. Yeah, so I assume that oh, the team sent the fan. Yeah. Yeah, I'm not sure what's going on. Where? Okay, let me just check what I see on my end. Okay, I just gave you the points manually. Yeah.
It's very interesting, but basically we get that it's scaling the testing more speed, and you're having to figure out the amount of ways.
So like likely it's so one way is like you're actually returning none. Another way that it will fail is if it's crashing. So the most common way that it's crashing is you're not opening the run simulator. So open file name. Okay. You know. So I posted the code. So have you tried running my code from that?
Yes, it did.
And what happened?
I believe it got split from
Right. So one situation where this happened is so like I was looking at one is like when people hard code file names to be something rather than file name, but they're not. Another is that people use like what you are doing. So instead of saying like
Yeah, I think
here
you're kind of like the first reason.
yeah. Yeah.
Then it also, that's why we're being so
Right.
So we have like any other ways maybe that it could be.
Well, so like in general, also it sometimes happens that the reason we're trying is because we have a global variable that's defined somewhere that is not defined in my code because like from a previous run or something you have something left. So one thing to try is run my test code up. Yeah. Yeah, actually genuinely not working. Yeah. Yeah, I'll see if I have. I'll see if I have time. Yeah. Right.
Does that mean the accuracy is 67.5%?
No, I mean, those are not kind of necessarily, like the 5 test cases, but some of them literally to check if like you're returning the quote when you should do it.
Right.
So it's like, well, like a chance that you return the quote.
So it doesn't necessarily mean the accuracy. 67.5.
I mean, accuracy, like you can definitely doesn't exactly 67.5, but in fact, that's not exactly accuracy.
Okay. So to compute the accuracy, you use the example you gave at the bottom of the video?
Yeah. Well, the accuracy very well, yeah. But like the accuracy is not also not how we do it.
Right. Oh, it's just recommended using things.
Well, it's not recommended. It's like if you code everything correctly, then it's telling you what the accuracy is. But I'm checking directly whether the functions are coded.
Whatever fried like overseas or fault means then
So like whatever we had last lecture, right? So we had kind of the linear thing, we had kind of the branching tree where the number of levels was log 2n, and then we had the branching where the height, so the number of levels was n.
so it's mostly about levels of like
Well, I mean, that's what we did. Like what I was doing there is I was just summarizing the lecture just before. Right, so like that's the things that we discussed like during the lecture. Yeah.
I have a question about like different.
Yeah.
It says return, like it's a non-type, it's pure return float, but when I run it on my end, it returns a float. So I'm not very.
I mean, it might be that it returns, so several things could happen. It could be that on your example, it returns a float, but in my example, it doesn't. Now, I gave you the example in the PLC, so you can just draw that.
So it's just like the small.
Well, it's like the specific case actually gave the case that I run, so you can just run it yourself. So another possibility is like it actually interprets none as like if the function crashes for one reason or another, then that also results in none.
Okay.
So the most common thing, not so one of the things that happens sometimes is people instead of saying file name, they say something specific. And then that's crashes because I don't get like the thing that you are using at the input, but that's not what you're doing. Another thing that sometimes happens, so again, like not sure what you're doing, so like for you it's crashes. But sometimes you have like return instead of an if statement, and then you don't always return the right thing. But what I would recommend is kind of as a start, just run the example that I've given on the beginning. And then like maybe it just shows the graph for that, and then I can just fix it.
I think I did this first one. This is better. I think this is the last Fridays.
Okay.
Recursion.
For today?
Last week, yeah,
Okay.
YMG last week.
YMG. Oh yeah. This one? Okay. Okay, I gave you the points.
Thank you.
Yeah.